In this discussion video, we will be reviewing average and instantaneous velocities and doing a practice problem. So let's let y equal s of t be the position of an object. So this is the position function of an object at time t. Okay, and I'm going to draw a picture. So I'm going to draw some axes. And I'm going to let these be the t, or the time axis, and the vertical axis is going to represent s of t, my position. And let's just say that my position function, when t equals 0, let's just say that my position was somewhere here, so some positive position. And then it goes like that, and it starts to curve upwards like this. Okay, and then somewhere down the road, let's have some time, which I'll call a. And if I label that point on the graph, this is the point A, comma, S of A. Alrighty, so let's first write down what the average velocity formula is. And remember, that is the change in position, or change in S, over the change in time. So I need some time interval over which I'm determining this average velocity. Okay, so I'm just going to pick a time a little bit further away from A. So I'll label that as B. And let's label the point on the graph where t is b. So I have b comma s of b, that's going to be the y value. Alrighty, so if I connect those 2 points with a line, we get this secant line, and it looks like something like this. So for the average velocity, change in s over change in t, if I work out what that is, this is s of b minus s of a on top. That's the change in position, over b minus a. That's the change in time. And notice that that's just the slope formula. In fact, this is the slope of the secant line. So the average velocity is the slope of the secant line, this line that we had drawn here. And if I want to estimate the instantaneous velocity at A, how fast is this object moving right at that instant where A occurs, I need to take the average velocity over a smaller and smaller time interval. In other words, I need to take this point B, and I need to move it closer and closer and closer to A. So as B gets closer and closer, as B gets closer and closer to that point A, our average velocity gets closer and closer to the instantaneous velocity. Instantaneous velocity. So the instantaneous velocity is going to be the slope of the tangent line. All right, so if I draw on a tangent line, I have to draw a line at A that sort of matches how steep the graph is right at that point. And it seems like that'll be something like this. Something like this. All right, so my slope of my tangent line, that is representing my instantaneous velocity. Alrighty, so let's look at an example. Okay, so this is the question. It's question number 4 from worksheet 2, and it says that the height of a ball in feet above the ground is given as h of t equals negative 16t squared plus 48t plus 64, where t is the number of seconds since the ball is thrown. Part A asks to find the average velocity between when the ball is thrown to when it hits the ground. B says find the instantaneous velocity when the ball reaches its highest point. So I want you to first pause the video for 3 minutes to try part A of this question. 4, 3, 2, 1, pause it and try part A. Alrighty, so hopefully you've done that. Hopefully you tried it for about 3 minutes. If not, really go ahead and do that now. It's super important to really test how well you understand these concepts by tackling these questions on your own first. All right, so A is asking us for an average velocity. So we need the change in position over change in time. In this case, my position function is called h for the height. So I'll need the final height, which I'll call h of b, minus the initial height, which I'll call h of a, over b minus a, where our time interval is from a to b. So the question says that the time we're talking about is between when the ball is thrown. So a is representing when the ball is thrown. And it's based off what the question tells us, t represents the number of seconds since the ball is thrown. So when the ball is thrown, that would be 0 seconds. Okay, so we know what a is. And then up until, then it talks about when it hits the ground. And we don't know when it hits the ground. So we need to find that. We need to find b, the final time, which is the time when the ball hits the ground, or time when the ball lands on the ground. Okay, so the ball is going to land. Remember, the height here is how many feet above the ground the ball is. So it lands when the height is 0. Let's set h of t, our height, equal to 0. So we'll get negative 16t squared plus 48t plus 64. That whole thing is equal to 0. And I could factor a negative 16 out of these terms. Negative 16, I'm left with t squared. And then minus 3t minus 4. Right, so 16 goes into each of these terms. And now this quadratic factors nicely. Let's see, it is t, and then I have a minus 4 plus 1. And at this point, I can go ahead and say what t is. T is either 4 from the first parentheses, or it's a negative 1 from the second parentheses. But negative 1 in this context doesn't make sense. When we're talking about a time in this problem, this doesn't make sense because the question says, well, t, time, is the number of seconds since the ball is thrown. So when the ball is thrown, that's 0 seconds. So based on the context, t in this problem is greater than or equal to 0. That's kind of the reference point from which we're starting to measure time, when t is 0. All right, so we know t is 4 when it lands. So our average velocity is h of 4 minus h of 0 over 4 minus 0. Okay, so there's a really quick way to figure out what h of 4 is. I actually don't need to plug that back in to h of t. If I wanted to plug 4 into here, I could. There's just a quicker way, which is to realize that when t equals 4, the ball lands. So this is when the ball lands. And when the ball lands, the height is supposed to be 0. That is what h of 4 is. It is just 0. And that's exactly what we figured out above. When we set the whole thing equal to 0, the height, we got that that's going to happen when t is 4. Okay, and then minus, now I do need to plug 0 into my height function. So let me put a big old parentheses around it so I don't forget to distribute the negative sign. If I plug in 0, we get negative 16 times 0 squared plus 48 times 0 plus 64, and then over 4 on the denominator. So this simplifies to, I'll get negative 64 over 4, and that becomes negative 16. And there are units here. On the top, it was units of height, which in this problem were feet, and units of time on the bottom, which were seconds. So this is in feet per second. That is my average velocity. All right, let's look at part B. Part B is asking, well, find the instantaneous velocity when the ball reaches its highest point. And this is something that we can sort of just conceptually figure out. There's not much computation actually to do here. So I want you to pause the video for just 1 minute and see if you can work out part B conceptually. 4, 3, 2, 1, pause it and try part B for a minute. Alrighty, so hopefully you did that. Hopefully you tried part B for about a minute. Let's talk about it together now. So if I think about the ground, and let's just say that this is the starting point for the ball. I know that the ball starts above the ground because when I plugged in t equals 0 to figure out its height at that starting point, this whole thing was 64. So I know that when it starts, it's 64 feet above the ground. Okay, and then it talks about its highest point. So we throw it, it reaches some highest point, and then it falls back to the ground, and then it lands. So at that highest point, the ball is momentarily still. Momentarily still. Which means our instantaneous velocity, I'll just abbreviate, instant velocity, should just be 0. There's going to be units, and they're feet per second for our purposes, but that is it. So that's what I meant by we can do this sort of conceptually. At that highest point, the ball is momentarily still, so our instantaneous velocity is 0.